Here's a summary of the entire chemistry paper 1 spec.
Atoms are the smallest parts of an element that can exist, and they make up every single thing in the universe. They're made up of 3 even smaller particles known as subatomic particles. These are protons, neutrons, and electrons. The center of an atom is known as the nucleus, and it contains just protons and neutrons. Surrounding the nucleus are the electrons which orbit around it. Protons have a positive charge with a mass of 1, neutrons have a neutral charge of 0 and also have a mass of 1, and electrons have a charge of -1 and have a mass that's very small. The nucleus holds nearly all of the mass of an atom, but is about 10,000 times smaller than the total size of it. Its radius is around 1 times 10 to the minus 14 meters, whereas for an atom it's around 1 times 10 to the minus 10. Atoms as a whole are neutral and have no overall charge. This is because they have the same number of positive protons and negative electrons. These charges cancel out, leaving the atom with the overall charge of 0. The atoms of an element can be represented by chemical symbols with 2 numbers. The bigger number is the mass number, which tells you the number of neutrons plus protons in an atom. And the bottom number is the atomic number, which tells you the number of protons. To find the number of neutrons, you need to subtract the atomic number from the mass number. An element is defined as a substance made up of one type of atom. There are over 100 different discovered elements which can all be found in the periodic table. Isotopes are defined as different forms of the same element with the same number of protons and different number of neutrons. This means they have the same atomic number but different mass numbers. Every element has its own relative atomic mass, and you can find them in the periodic table as the bigger number. The relative atomic mass takes into account something called the abundance of the element. The abundance is basically how common a particular isotope of an element is if you were to have a sample of it. So to calculate the relative atomic mass of an element, you need to multiply the mass number of each isotope by its abundance. Then you add all of these up and divide the sum by 100. Mixtures and compounds are both made up of 2 or more substances. The difference between them is that in compounds the substances are chemically combined, but in mixtures they're not chemically combined. Another difference is that the components within a mixture retain their chemical properties, whereas in a compound they do not. Compounds are difficult to separate into their original components and can only do so by using chemical reactions. Mixtures, on the other hand, can be separated using physical methods, and there are 6 of these separation methods you need to know. The first is filtration, which is used to separate an insoluble solid, which means a solid that can't dissolve, from a liquid. An example of this would be sand and water. You add a piece of rolled up filter paper into a funnel and place that on a conical flask. When you pour the mixture in, the water will pass through the small holes in the filter paper and get collected in the conical flask. This is known as the filtrate. The sand will remain on the filter paper, and this is known as the residue. The second and third examples are evaporation and crystallization, which are both used to separate soluble solids from a liquid solvent. So this could be things like salty water. In evaporation, the mixture is added to an evaporating dish and heated until the water evaporates and you're left behind with dry crystals of the salt. But some crystals decompose when you heat them, so you need to use crystallization instead, which has a very similar method with some extra steps at the end. When heating the mixture and the crystals start to form, you take the heat off and leave it to cool. This causes even more crystals to form, which can be filtered out and left to dry. The fourth example is simple distillation, which is used to separate mixtures of liquids with different boiling points. An example would be water and ethanol. The mixture is heated to the temperature of the lowest boiling point of the 2, which is 78 degrees in this example. This causes just the ethanol to boil into a gas, and the water stays behind as it hasn't reached its boiling temperature. The ethanol vapor then passes through a condenser where it condenses back into a liquid and is collected in a beaker. Fractional distillation is similar to simple distillation, but it's used to separate a mixture of more than 2 liquids. It involves a fractionating column with glass rods in it, which has a temperature gradient. This is just when the temperature is hot at the bottom and cooler at the top. This helps to improve the efficiency of the separation of the liquids. So for example, if you had a mixture of methanol, ethanol and water, you would first heat the mixture up to 65 degrees to evaporate, condense and collect the methanol. You would then raise this temperature to 78 degrees and repeat to collect the ethanol. You can keep repeating this process for several liquids. The final example is chromatography, which is used to separate and analyze the components in a mixtures like dyes in an ink. You start off by drawing a pencil line near the bottom of a piece of filter paper and place a spot of ink on it. Then you place a piece of paper in a beaker of a solvent such as water. The water will rise and separate out the dyes in the ink based on how soluble they are. These form spots on the paper which can be analysed. The model of what we think atoms are has developed throughout history due to the discoveries of many different scientists. It all started in 1803 where John Dalton proposed that atoms were solid spheres and different elements had different types of these spheres. By 1897, J.J. Thomson carried out experiments which led him to discover electrons. He proposed a new model for the atom known as the plum pudding model, and this showed the atom as a sphere of positive charge with electrons embedded within it. A few years later, Ernest Rutherford and his student Ernest Marsden conducted the alpha particle scattering experiment which disproved the plum pudding model. During this experiment, they fired positively charged alpha particles at a thin piece of gold foil. It was so thin that they could assume that it was only 1 atom thick. While carrying it out, they found that nearly all of the alpha particles passed straight through the gold foil. This told them that most of the atom must be made out of empty space, as there was nothing to stop them. The second observation they made was that there was a very small number of alpha particles that were deflected. This showed that the mass of an atom must be concentrated in a very small positive region, which we call the nucleus. The plum pudding model did not explain any of these observations, so the nuclear model was proposed, which showed a central dense nucleus with a cloud of electrons around it. In 1913, Niels Bohr discovered that electrons could only occupy certain orbits at fixed distances from the nucleus, which we call shells or energy levels. Bohr carried out further experiments which showed that the nucleus could be subdivided into smaller positively charged particles, which we call protons. All his theoretical calculations agreed with his experimental observation, which confirmed his model. Around 20 years later, James Chadwick discovered neutral particles in the nucleus, which we call neutrons, and this led to the model that we use today. Electrons in an atom orbit around a nucleus in shells or energy levels, and they determine the chemical properties of the atom. These shells are filled from the lowest energy level, which is closest to the nucleus, to the highest energy level, which is the furthest. The first shell can hold up to 2 electrons, and the second and third shell can each hold up to 8 electrons. You can represent the electron configurations of an atom by using diagrams or as numbers indicating how many electrons there are in each shell. The periodic table contains all the elements that exist and has developed a lot over the years. In the early 1800s, elements were organized by atomic weight and their physical and chemical properties. Back then, atomic weight was the only measurable data that early scientists could use. This is because protons, neutrons and electrons had not been discovered yet. This led to the creation of early periodic tables where properties kept repeating periodically, hence the term periodic table. But these early periodic tables were incomplete and some of the elements were placed in inappropriate groups. This is because scientists were placing them strictly according to their atomic weights. But in 1969, Dmitry Mendeleev improved these earlier tables by arranging the 50 known elements at the time by atomic weight and also based on their properties. He did not force elements into groups that didn't fit the patterns. Instead, he made 2 changes. The first was that he left gaps for elements that he thought would fit the groups but had not been discovered yet. So for example, he predicted the existence and properties of an element that did fit a gap and called it Eka aluminium. And this was later discovered and we now call it gallium. The second change that Mendeleev made was that he changed the orders of some of the elements, even if their atomic weights didn't fit the order. For example, iodine should be placed before tellurium in the periodic table if it was arranged by atomic weight. But Mendeleev switched their orders because he found that iodine's properties were more similar to the other elements in his column if it was placed after tellurium. These 2 types of changes turned out to be the right thing to do. This is because the elements he left gaps for were discovered later and fitted the patterns he had predicted. As well as this, the discovery of isotopes in the early 20th century confirmed all his decisions not to place the elements in a strict order of atomic weight. So eventually, Mendeleev's periodic table developed into the modern periodic table that we use today. It's based on increasing atomic number instead of atomic weight, and it shows repeating patterns in properties. Metals are located on the left and non-metals on the right, and these 2 are separated with a staircase line. The vertical columns in the periodic table are known as groups, and they correspond to the number of electrons in the outer shell of an atom. And because of this, the elements in the same group have similar chemical properties and react similarly. The horizontal rows, on the other hand, are called periods, and they represent the number of shells that an atom has. Going down the periodic table can allow you to make predictions about other elements in the same group, as there are usually observable trends. When looking at metals, for example, the metals further to the left of the periodic table have fewer electrons to remove from their outer shell, and this makes them more reactive. As you go down a group, the outer shell electrons are further away from the nucleus because the atom's getting bigger and has more shells. This decreases the attraction of the electrons to the nucleus, which makes the electron easier to remove, meaning the metal is more reactive. This means that the reactivity of metals increase as you go down the group, as it's easier for elements to react and lose electrons. When looking at non-metals on the other hand, the ones found further to the right have more outer electrons. And as you go down a group in non-metals such as group 7, the outer shell electrons are further away from the nucleus just like in metals, meaning they still have less attraction. But in metals, electrons are being gained and not lost. So less attraction means it's more difficult to gain the electrons, which means it makes them less reactive. So this means the reactivity of non-metals like group 7 elements decrease down a group as it's more difficult for elements to react and gain electrons. Another difference between metals and non-metals are their physical properties. Metals are generally really good conductors of heat and electricity, and they have high melting and boiling points, whereas non-metals do not conduct electricity and heat very well and have low melting and boiling points. The group 1 elements are known as the alkali metals, and they all have one electron on their outer shells, which means they're all reactive and have similar properties. The reactivity of group 1 metals increase as you go down the group. Another trend you observe is that as you go down the group, the melting and boiling points of the group 1 elements decrease. Now there are 3 types of reactions that you need to know for the group 1 metals. The first is the reaction of the metal with water. When they react, the alkali metals form metal hydroxides and hydrogen gas. These reactions are very vigorous and even more violent as you go down the group. So for lithium, for example, you would see it melt into a ball and float around on the surface of the water with hydrogen gas bubbles being given off. But if you were to use sodium instead of lithium, more bubbles will be released. If you use potassium instead, which is even further down the group, the reaction would be so violent that the ball of metal will catch fire with a lilac flame while it floats around in the water. The second reaction you need to know about is with chlorine. Here a metal chloride is formed, which are white salts. Just like with water, these reactions get more vigorous the further down the group you go. As an example, if we looked at sodium reacted with chlorine, we would form the salt sodium chloride. The third reaction you need to know about is with oxygen, where the alkali metal forms a metal oxide. This naturally happens to the alkali metals when they're exposed to air. They're normally shiny metals, but they're so reactive that they react with the oxygen in the air to give a dull coating of the oxide. So if you expose lithium to the air, it would react with the oxygen to form lithium oxide. The group 7 elements are known as the halogens, and they all have 7 electrons on their outer shell. Just like alkali metals, this means all the halogens have similar chemical properties. They're found naturally as diatomic molecules, which means they exist as 2 atoms bonded together. So that would be F2 for fluorine, Cl2 for chlorine, Br2 for bromine, and I2 for iodine. As you go down the group, the boiling point of the halogens increase. The reason why is because the number of electrons in the molecules increase. This means there are stronger intermolecular forces between the molecules. And this means that more energy is required to overcome these intermolecular forces. The color of the halogen also gets darker as you go down the group. Fluorine is a yellow gas, chlorine is green, bromine is a red-brown liquid, and iodine is a grey solid. As you go down the group, the reactivity of the halogens decrease. When halogens react with non-metals, they form simple molecular substances with covalent bonds. So for example, chlorine reacts with hydrogen to form hydrogen chloride. When halogens react with metals, on the other hand, they form ionic compounds with ionic bonds. An example of this would be when chlorine reacts with sodium to form sodium chloride. Another type of reaction that halogens undergo are displacement reactions. These are reactions where a more reactive halogen replaces a less reactive halogen in a compound. So for example, if chlorine reacts with potassium bromide, as chlorine is more reactive than bromine, it will replace it to form potassium chloride and bromine. If the halogen is less reactive than the one in the compound, it will not replace it, so the displacement reaction will not occur. Here's a summary of all the possible displacement reactions and the observation you'd see in them. The group 0 elements are known as the noble gases, and they have full outer electron shells. These full shells make them very stable so that they're inert, which just means that they're not reactive. They're also colorless at room temperature. This stability also means they exist as single monatomic atoms, unlike diatomic atoms for group 7 elements. This is because they don't need to gain or share electrons, as they already have a stable full outer shell. The boiling point of noble gases increases as you go down the group. This is because the number of electrons in the atom increases. This makes the bonds between the atoms, known as intermolecular forces, stronger. The stronger bonds mean that more energy is needed to break these intermolecular forces, which means the boiling points will get higher. Ions are atoms or groups of atoms that have lost or gained electrons and have a charge. Metals lose electrons to form positive ions, which we call cations, and non-metals gain electrons to form negative ions or anions. Ions are formed when electrons are transferred between atoms to achieve a full outer shell, and this full outer shell makes them more stable. You can usually predict what type of ion an atom will form by knowing the group of the element that it's in. Group 1 elements form +1 ions, Group 2 elements form +2, Group 6 form -2, and Group 7 form -1 ions. All the other groups have more complicated rules that you don't need to memorize. Ionic bonding is a type of bonding that occurs between a metal ion and a non-metal ion. It involves the transfer of electrons from a metal atom to a non-metal atom. The metal atom loses electrons to become a positively charged ion, while the non-metal atom gains those electrons to become a negatively charged ion. These oppositely charged ions are then strongly attracted to each other by electrostatic forces, and these forces are what we call the ionic bond. You can represent ionic bonds using dot and cross diagrams. These represent the arrangement of electrons in atoms or ions where each electron is symbolized by a dot or cross. So as an example, let's look at lithium fluoride. Lithium has 1 outer shell electron and fluorine has 7. The best way for both atoms to get a full outer shell is for lithium to transfer 1 electron to fluorine. This gives both atoms full outer shells and makes them stable. As lithium loses 1 electron, it gets a charge of +1, and fluorine gains 1 electron, so it gets a charge of -1. Both of these ions are oppositely charged and they have electrostatic forces of attraction that holds them together. This is known as the ionic bond. The Li+ and F- ions join to give a final formula for lithium fluoride as LiF. Ionic compounds are formed when metals and non-metals combine with ionic bonds. They exist in a giant ionic lattice structure, which is basically a 3D cubic structure, where the positive and negative ions are held together by strong electrostatic forces of attraction between them. There are 4 key properties of ionic compounds that you need to know about. The first is that they have high melting and boiling points, and this is due to the strong electrostatic forces of attraction between the oppositely charged ions, which need a large amount of energy to overcome. The second property of ionic compounds is that they're soluble in water, which means they dissolve in water and create a solution. The third property is that ionic compounds conduct electricity only when they're molten or aqueous. This just means when they're liquid or dissolved in water in a solution. When they're in these states, the ions in them are free to move so they can carry a charge. So this basically means they can conduct electricity. When they're in a solid form, on the other hand, the ions are fixed and are not free to move. This means they can't carry a charge and therefore do not conduct electricity in this state. This is the final property. Covalent bonding is bonding that occurs between 2 non-metals. It involves atoms sharing pairs of electrons so that they can achieve a full outer shell and become stable. These bonds form because the positively charged nuclei are attracted to the shared pair of electrons by electrostatic forces. Covalent bonds can be represented using dot and cross diagrams, and these show the outer shells of the atom overlapping. Any electrons that are being shared are drawn in the overlapping section of the shells. So for example, if we had hydrogen, drawing a dot and cross diagram for a single hydrogen atom shows that there's only 1 electron in the outer shell. And as this is the very inner shell, it only holds 2 electrons. So you'd only need 1 more electron to get a full outer shell. So what you'll do is get another hydrogen atom and share the electrons. When this is done, you can see that the left atom has a full outer shell of 2, and so does the right one. This all makes the structure stable and forms a molecule of hydrogen, or H2. Here are some more common examples of covalently bonded molecules. Simple molecular substances are made out of small molecules formed by covalent bonds. There are 2 types of bonds involved. The first are covalent bonds, which are found between atoms. These bonds are very strong and need a lot of energy to break. The second type of bonds are intermolecular forces, which are forces between molecules. These are much weaker than covalent bonds and do not need as much energy to break. When simple molecular substances melt or boil, it's the intermolecular forces that need to be broken, not the covalent bond. And because these are weak, only a small amount of energy is needed to overcome them. This gives simple molecular substances low boiling and melting points, and it explains why they're usually found as liquids or gases at room temperature. Simple molecular substances do not have an overall electric charge, therefore they do not conduct electricity because they don't contain free moving electrons or ions. The second type of covalent compounds are polymers, which are long chains made up of many repeating units known as monomers. The atoms within them are held together by covalent bonds, and these create large molecules with a lot of electrons. This gives them strong intermolecular forces which require a lot of energy to break. This means that polymers have high melting and boiling points when compared to simple molecular substances. This means they exist as solids at room temperature. The third type of covalent compounds are giant covalent structures. These are structures where atoms are bonded in a large network of covalent bonds. Diamond is formed from several carbon atoms, each sharing 4 covalent bonds in a tetrahedral structure. It's very hard with a high melting point because the large network of covalent bonds require a large amount of energy to break them. Diamond does not conduct electricity because it has no free moving electrons or ions. Graphite is made of layered structures of hexagonal rings, and here each carbon atom is bonded to 3 other atoms with covalent bonds rather than 4. So because carbon has 4 electrons in its outer shell, only 3 of them will be used to bond to other atoms, and this means that the 4th electron is not used for bonding. This electron is delocalized and free to move. This means that graphite is a good conductor of electricity, as its delocalized electron can carry a charge through its structure. It's also soft and used as a lubricant due to the weak forces between the layers. These weak forces allow the layers to slide over each other. Graphene, on the other hand, is a single layer of graphite, and it's strong and light. It's a good conductor of both heat and electricity, again due to its delocalized electrons, so it's used in electronics and composite materials. Fullerenes are molecules with hollow shapes such as spheres and tubes. They can encapsulate other molecules and are used in drug delivery and industrial catalysts. One example of a fullerene is Buckminster fullerene. This is a fullerene in the shape of a sphere with a formula of C60. Another example of a fullerene are carbon nanotubes. These are cylindrical fullerenes with high length to diameter ratios. Their properties make them useful for nanotechnology, electronics and materials. They're good conductors of heat and electricity as they have delocalized electrons, meaning they can be used in electronics and nanotechnology. They also have very high tensile strength without much mass, meaning they're useful for certain materials that need to be strong and light, such as the ones used in tennis rackets. Metallic bonding is bonding that occurs between metals, and within metals the outer shell electrons are delocalized and free to move. This creates a sea of delocalized electrons. Within this sea of electrons, there are positive metal ions which are arranged in a regular pattern in a giant lattice structure. These positively charged metal ions and negatively charged sea of electrons have electrostatic forces of attraction between them, which form the metallic bonds that hold the whole structure together. Metals have 4 main properties that you need to know about. They have a high melting point, and this is due to the strong electrostatic forces of attraction between the positive metal ions and the negative sea of delocalized electrons. This electrostatic force of attraction requires a large amount of energy to break. This means their melting points are high and explains why metals are generally solid at room temperature. The second property is that metals are good conductors of electricity. This is because the delocalized electrons within it carry an electrical charge through its structure. Similarly, they're also very good conductors of heat, and that's because the delocalized electrons can carry thermal energy through its structure. The final property is that pure metals are malleable. This basically means that they can be bent or shaped without breaking, and that's due to their structures, which consists of layers of atoms that can slide over each other. But this means that pure metals are usually too soft for many uses, so to make them harder and more useful, they're turned into alloys. Alloys are basically mixtures of different metals. They're harder than pure metals because they have different sized atoms within them, which means they're not arranged neatly in layers. Or in other words, the layers are distorted. This makes it more difficult for them to slide over each other. There are 3 states of matter that you need to know about, and they're solid, liquid, and gas. They can be represented using a simple model which shows solids with spherical particles which are closely packed in a regular structure. These particles vibrate about a fixed position and have very strong forces or bonds between them. This means solids keep a fixed shape and cannot be compressed. Liquids also have closely packed particles. However, these are not in a regular structure and they are free to move. They have weaker forces between the particles. This means liquids do not keep a fixed shape, and because their particles are still very close together, it's hard to compress them. Gases have particles that are far apart in an irregular structure with particles that move rapidly in random directions. They have the weakest forces between the particles of the three states, and they can't keep a fixed shape but can be compressed. Substances can change states between solids, liquids and gases, and these processes involve energy changes and particle movement. So when a solid is heated to its melting point, its particles gain energy and vibrate more. This weakens the forces holding them together. This process is known as melting, and it turns solids into liquids. Heating a liquid further to its boiling point gives the particles even more energy to move even more faster. This leads to boiling or evaporating, where the liquid becomes a gas. If we go the other way around and we cool a gas down to its boiling point, the particles lose energy and form bonds. This causes the gas to turn into a liquid and is known as condensing. When the particles in a liquid are cooled even more to their melting point, they lose more energy. This causes them to move less and form more bonds between them, causing the liquid to become a solid, and this process is called freezing. The MR of a substance is also known as the relative formula mass, and it's basically the sum of the relative atomic masses, or ARs, of all the atoms in a chemical formula. So to work out the MR of any compound, you need to add everything together. As an example, let's try and find out the MR of calcium fluoride, or CaF2. So that's 40 plus 19 times 2, and this gives a final answer of 78. Here are a few more examples that you can try yourself. The conservation of mass states that in any reaction, mass cannot be created or destroyed. So that means the total mass of the reactants should always equal the total mass of the products. The mole is a measurement of the amount of a substance. And if you have 1 mole of any substance, it has the same number of particles as Avogadro's constant. Avogadro's constant is 6.02 times 10 to the 23 per mole. So that's the number of particles in 1 mole of a substance. The particles mentioned in this definition can be atoms, molecules, ions, and even electrons. 1 mole of any substance also has the same mass in grams as its own relative atomic mass or relative formula mass. So what that means is if you had 1 mole of carbon, for example, it would have a mass of 12 grams, because that's the relative atomic mass of carbon in the periodic table. If we looked at water as another example, it's H2O, and its MR is 1 plus 1 plus 16. So that gives 18, which means that 1 mole of water would always have a mass of 18 grams. You can find the number of moles of any substance by using the formula moles is equal to mass over MR. Moles can be used in chemical equations to calculate masses of reactants and products by using a few steps. Let's try this question as an example to show these steps. The first thing to do is to identify the known and unknown in a question. The known is the substance that you know the mass of, and the unknown is the substance you're trying to find out the mass of. So in this example, the known is sodium, as we know there's 46 grams of it, and the unknown is the mass of sodium oxide. The next thing to do is to find the moles of the known substance. You can do this by using the formula and dividing the mass by the MR of the known substance. So here we would do 46 divided by the MR of sodium, which is 23. This tells us that there are 2 moles of sodium involved. The next step is to find the moles of the unknown, and this is done by looking at the big numbers in front of the reactants and products in the balanced equation. You need to use the number in front of the known and the unknown to write a ratio for them. You can use this to find the moles of the unknown. So in this example, the big number in front of the known and the unknown are 4 and 2, meaning we have a ratio of 4 to 2. This can be simplified to a ratio of 2 to 1. So this means your moles of your known substance is 2 times bigger than the moles of your unknown substance. So if you have 2 moles of sodium, which is your known, you need to divide it by 2 to find the moles of sodium oxide. And in this case, this would give 1 mole of sodium oxide. Now that we know the moles of the unknown, we need to find the mass of it by using the moles equation again. But this time, we rearrange it to give mass is equal to moles times MR. This would be 1 mole multiplied by the MR of sodium oxide, which is 23 plus 23 plus 16, which gives a final answer of 62 grams. You can also use moles to balance equations if you know the mass of the reactants and products. You start off by dividing the mass of each reactant and product by the MR to find their moles. Then you divide each of them by the smallest number out of them all, and this will give you the coefficients that will allow you to balance the equation. In some chemical reactions, you can have an excess reactant and a limiting reactant. When you have an excess of a reactant, you have more of it than is needed for the reaction, whereas a limiting reactant, you have less than needed. A limiting reactant is the substance that is completely used up before the excess reactant. To find out which of the reactants are the limiting reactant, you need to turn the mass into moles by using the formula and dividing it by MR. You can then compare these to the balancing coefficients in front of the reactants and see which one is in excess. To find the concentration of a solution in grams per dm cubed, you can use the equation mass over volume. And to use this equation, remember to convert from centimeters cubed to dm cubed by dividing by 1000. Next up, we have the reactivity series, where the higher up an element is, the more violently it will react with water and acid. The reactivity series is useful in metal extraction. Most metals are naturally found as metal oxide in rocks known as ores. In order to extract the metal out, carbon can be used to reduce the metal oxide to form a metal and carbon dioxide. However, this method can only be used for metals that are less reactive than carbon. To extract metals that are more reactive than carbon, electrolysis needs to be used because the carbon is not reactive enough to remove the oxygen from the ore. But electrolysis is a much more expensive process as electricity is needed for it. Oxidation can be defined as either the gain of oxygen or the loss of electrons, and reduction can be defined as the loss of oxygen or the gain of electrons. An example of redox reactions are displacement reactions. From the normal equations here, you can write the ionic equation by splitting the compounds up into their ions. In this particular example, zinc is going from Zn to Zn2+, which means it's losing electrons, and this tells us that zinc is being oxidized. On the other hand, copper is going from Cu2+ to Cu, which means it's gaining electrons, and this tells us that copper is being reduced. Both of these can be represented as half equations which show the movement of electrons, one for reduction and one for oxidation. Next up, let's talk about the pH scale, which measures how acidic or alkali a solution is. A pH from 0 to 6 indicates an acid, a pH from 8 to 14 indicates an alkali, and anything with a pH of 7 indicates a neutral solution. Universal indicator can be added to a solution to find its pH. It changes color, and from the color you can predict its pH. A less subjective way to measure pH is by using a pH probe, which gives you an actual digital reading of the pH. Acids release hydrogen ions in solution, whereas alkalis release hydroxide ions. The reason acids release H+ ions in the solution is because when they dissolve in water, they ionize, which basically means they break up into their ions, and these ions always include H+ ions. Strong acids such as hydrochloric, nitric, and sulfuric acid fully ionize in water, which means all the acid particles in the solution break up into their ions, which usually means they have lower pHs. Weak acids, however, only partially ionize, as only some of their particles break up into ions, and this usually means they have higher pHs. This is because there are fewer H+ ions released into the solution, which means the H+ ion concentration is lower. The relationship between H+ ion concentration and pH concentration is that if you increase the H+ concentration by 10 times, the pH decreases by 1. So using this rule, you can predict the pH change of a solution by seeing how much its H+ concentration changes by. Whenever an acid reacts with an alkali, a neutralization reaction occurs, which forms salt and water. Any neutralization reaction can be written as an ionic equation where the H+ from the acid and the OH- from the alkali react to form H2O. You can work out the type of salt formed if you know the acid used in the neutralization reaction. Hydrochloric acid forms chlorides, nitric acid forms nitrates, and sulfuric acid forms sulfates. So when you react a metal oxide or a hydroxide with an acid, you get salt and water formed. But when you react a metal carbonate with an acid, you get salt, water, and carbon dioxide being formed. Electrolysis is the process of breaking up an ionic compound using an electric current. The setup involves a battery, 2 electrodes, and an electrolyte. The electrolyte is the ionic compound that's being separated, and this needs to be either molten, which means melted to liquid, or aqueous, which means dissolved in water. This is so that they can conduct electricity for electrolysis. They can only conduct electricity in this state because the ions are free to move. The electrodes used in the setup are usually made of graphite, and there are 2 types. The anode is the positively charged electrode, and the cathode is the negatively charged one. When current flows through the setup, the cathode attracts the positive ions in the electrolyte, and when it reaches the electrode, reduction occurs. This is where the positive ion gains electrons to form the product. At the anode, the opposite occurs. For molten electrolytes, the product formed are always the elements in the compounds. So if the electrolyte is molten sodium chloride, for example, the products formed are sodium and chlorine. That's because the sodium ions go to the cathode and gain electrons to form sodium metal, and the chloride ions go to the anode and lose electrons to form chlorine gas. For aqueous electrolytes, figuring out the products are a bit more complicated. This is because there are additional ions in the solution that come from water. That's because water ionizes to release H+ and OH- ions in the solution. So if we had aqueous sodium chloride as the electrolyte this time, the ions in the solution will still be Na+ and Cl- like before, but this time there will also be extra H+ and OH- ions, and these come from the water. To figure out what gets formed at each electrode, there are two sets of rules that you can use. At the cathode, the rule is that the less reactive element out of the two positive ions will always get formed. So in this case, hydrogen is less reactive than sodium, therefore hydrogen gas will be formed at the cathode. At the anode, however, the rule is that if a halogen is present, it will always get produced. But if a halogen is not present, oxygen will get produced instead. So in this example, as chlorine is a halogen, chlorine gas will get formed at the anode. One specific example you need to memorize is using electrolysis to extract aluminium from an aluminium oxide ore. For this electrolysis, the aluminium oxide is mixed with cryolite and melted to make a molten electrolyte. The reason cryolite is used here is because it lowers the melting point of the mixture, which makes it cheaper to melt. In this example, as the electrolyte is molten, aluminium is formed at the cathode as a liquid and oxygen is formed at the anodes. The graphite anodes used in this need to be replaced regularly as the oxygen formed reacts with the carbon in the graphite to form carbon dioxide. This slowly wears the anode away, meaning it needs to be replaced regularly. Next up, we have energy changes in reactions, where all reactions can either be exothermic or endothermic. An exothermic reaction is a reaction where energy is released to the surroundings, and these show a rise in temperature. Examples of these are combustion and neutralization reactions, and practical uses of these include hand warmers and self-heating cans. Endothermic reactions, on the other hand, absorb energy from the surroundings and show a fall in temperature. An example of this are thermal decomposition reactions, and a use includes sports injury packs. All reactions can be represented on reaction profiles, which are graphs which show how energy changes with the progress of a reaction. In an exothermic reaction, the energy of the reactants are higher than the product as the lost energy gets released to the surroundings. But for the reaction to occur, it must overcome the activation energy of the reaction. This is the minimum energy required for the reactant particles to successfully collide and react. This is represented on a reaction profile with a hump. The overall energy change is the difference between the energy of the reactants and the energy of the products. For endothermic reactions, the opposite occurs and the products are higher than the reactants, and the activation energy is represented by this, and the energy change is represented by this. During any reaction, there are always two processes that occur: bond breaking and bond forming. Bond breaking first occurs where all the bonds of the reactants are broken using energy, and this process is endothermic as it takes in energy. The atoms are then rearranged, and bond forming occurs where new bonds are created to form the final products. This process is exothermic and releases energy. In an exothermic reaction, more energy is released during bond forming than is taken in bond breaking. Whereas in an endothermic reaction, more energy is taken in during bond breaking than is released during bond forming. You can use this concept to carry out bond energy calculations to find the energy change in a reaction. This is done by finding the energy needed to break the reactant bonds and subtracting it by the energy released during bond forming. Here's an example of one of these.